Let's prove the chain rule. The chain rule is easy to prove. It's only a little bit harder to prove correctly. There's such a tempting wrong proof that I want to start with that. So I've prepped the board here with an incorrect proof of the chain rule. Let's start with the statement of the chain rule. The derivative of the composition of functions f of g of z is equal to f prime of g of z times g prime of z. You differentiate the outside, hold the inside fixed, you multiply by the derivative of the inside. Here's a wrong proof of the chain rule. We take the derivative of the composition. This is just another way of saying the derivative of f of g of z. I've got an x in here because I tend to write x's accidentally. Okay, so that's going to be at z. That's not the error with the proof, obviously. We get the limit. This is the limit definition of the derivative. This step is correct. The step is correct. This is the definition of the derivative. So if I say that a proof is wrong, then I should be careful about which step is wrong. This step of the proof is correct. We just apply the definition of the derivative of the composition of the two functions. So the next step is very interesting and clever strategy. The next step is to multiply and divide strategically by g of w minus g of z. The reason for this is because so basically we're taking this fraction, separating it and putting it here, and we're multiplying and dividing by g of w minus g of z. This term will quickly become the derivative g prime of z that we're looking for and expecting at the end of this computation. This term will turn into f prime, but f prime at g of z. So let's look at that closely and we'll see how that works, because understanding this wrong proof is actually going to be instrumental to understanding the right proof. So let's look closely at how this works. This is not, so when we split this term this way and then split the limits and then look at this limit, this is not the definition of the derivative, right? If it were the definition of the derivative, it should have simply a w here instead of a g of w, and it should have simply a z here in place of the g of z. Well, the fact that this is a g of z instead of a z means that this is not the derivative f prime of z, but the derivative f prime of g of z, which is actually what we expect. So that's actually kind of to be expected, that instead of looking at f of z and minus z, that we should have a g of z there because we're expecting to get the limit of f prime at the value g of z. Why is there a g of w instead of a w, and does it make a difference? Well, it actually doesn't make very much difference that there's a g of w instead of a w, because as w approaches z, what does g of w do? As w approaches z, g of w approaches g of z. And so here, this g of w here is acting like a variable that is approaching g of z. And so, superficially, no worries, this thing will act like the derivative f prime of g of z. The problem is g of w approaches g of z a little bit too well, at least in theory it might. In theory, even when w is approaching z but not equal to z, g of w could be equal to g of z. So what's the big deal? Well, the big deal is if g of w equals g of z, then the step of multiplying and dividing by g of w minus g of z, which is the step of multiplying and dividing by 0, was algebraic nonsense, and this doesn't make any sense. And furthermore, if that were to happen, this limit would not exist. And so if we have some sort of guarantee that g of w is not g of z, then we can follow this proof, and this proof essentially works. But without such a guarantee, this proof really doesn't hold. And so we need to make some modifications to this proof. In order to make them, before we make them, I want to remind you of a couple of things. First of all, we have this limit law, which was limit law 5 or 6 in a list of limit laws. And we're gonna need this. This is saying that if an inner function has a certain limit, as x approaches x naught, it has a limit of y naught, then the composition also has the limit, and the limit is f of that limit. That is provided the outer function is continuous at that value. We're going to be using this. And I also want to point out something peculiar that you can do with the quotient in a derivative here. If you have, so the function f of z minus f of x minus z over z minus x, this is obviously inspired by the derivative f prime of x, but it's a little bit different. It doesn't have the limit, right? So this quotient function is not defined when z equals x, but as a function of z, it can be completed. You can convert this quotient function to the function which is equal to this when z is not x, but equal to f prime of x when z is equal to x. So this function q, which I've defined in this way to be q for quotient, it's this quotient that appears in the derivative if z is not x, and it's actually the derivative if z equals x, then q is continuous at x. It's actually, provided that f is, q is, so this assumes, actually, I should add the assumption that f prime exists. So q is continuous at x if f prime exists. And is furthermore continuous at all the other points, provided that f is continuous at those points too, because it's just made out of f and the division by this, but so long as z is not equal to x, then this thing will be a continuous function too. So this function is continuous at x, provided that f prime exists. We will leverage that fact indirectly. So let's return to the proof of the chain rule here. The error was the introduction of g of w minus g of z in the numerator and in the denominator, expecting them to cancel, neglecting the possibility that g of w minus g of z might be 0. And so what we're going to do is so there are actually a lot of ways around here. One way to do this is to say, there are two cases. One case in which g of w minus g of z is frequently 0 as w approaches z, and then the other case in which that can be excluded. And then we split the chain rule into two cases, and that works. You can find a lot of proofs that take that form in various textbooks. Another way of getting around the problem is to use the tangent line approximation. This is a pretty good strategy. The tangent line approximation gives you a means to approximate both functions by linear functions, and then you have to make an argument that the resulting combination of the tangent line approximations really does work out to predict the tangent line approximation of the result. That's a good proof too, and you can find that in various textbooks. The proof that we're going to use is going to be sort of motivated by this strategy, that a quotient, particularly one of the quotients that appears this way, can kind of be completed by adding in the derivative here. And so let's look at this strategy. What we're going to do is we are going to attempt to multiply and divide by g of w minus g of z, just as this proof does. But instead of doing so literally, we're going to add a bailout condition for what happens when g of w minus g of z is actually equal to 0. So I'm going to multiply and divide by the same thing. And I'm going to write this in this notation because I'm really defining a piecewise function here. So I'm going to define a piecewise function and sort of an unnamed anonymous piecewise function here. And that may be too big. And the value of the function is going to be f prime of g of z if g of w equals g of z. And it's going to be this thing that I actually want it to be if g of w is not equal to g of z. So basically here, what I'm trying to do is I'm trying to account for the possibility that this denominator might go haywire. And I'm trying to make the function do the right thing if the denominator goes haywire. The right thing is going to be inspired by the expectation of what that limit is supposed to do. The right thing is going to be, well, it should give you the derivative, which is what this thing should be approaching anyway as w approaches z. So I'm going to take this entire function here, and I'm going to multiply that by g of z minus, I should write g of w. So g of w minus g of z over w minus z. And then out here, I get the limit as w approaches z. Now, have I messed anything up yet? Well, so here I've taken this simple quotient and I've replaced it with this. And you might say problem solved. But wait a minute, the original act of multiplying and dividing by g of w minus g of z was motivated by the assurance that we were multiplying and dividing by the same thing. And when you multiply and divide by the same thing, well, then you don't change the expression, right? Here, I've replaced something with something far more complicated. And where's my guarantee that this thing is actually equal to this, right? I mean, I need some sort of guarantee that that's the same as that now. So let's worry about that first. So is this really equal? Well, there are two cases. The cases are if g of w equals g of z and if it doesn't, okay? So the first case is if g of w is not equal to g of z. So in this case, the introduced denominator is not 0. So then g of w minus g of z is not 0. And then if we're in the case when this is non-zero, so if g of w is not equal to g of z, then this function here, this piecewise defined function, will take its first condition and will become equal to this, right? It will not become equal to this, and we can ignore this because in the case when g of w is not g of z, we will take this value. And then its denominator will be non-zero, fortunately, and it will cancel this. So the terms g of w minus g of z cancel. And when they cancel, we see that we actually get this thing, right? So the first case, when g of w is not equal to g of z, these things are equal because this thing is, in that case, guaranteed to be non-zero, and so they will cancel. In the second case, if g of w is equal to g of z, well, then what happens? Then we're actually equal to f prime of g of z. Is f prime of g of z guaranteed to exist? Yes. By the presumption in the very premise of the chain rule, that term is guaranteed to exist. So we don't need to worry about existence of this term. What will this thing be? So we get f prime of g of z times, and then what do we get here? Here we get 0. Because in the case when g of w equals g of z, then this thing is simply equal to 0. And so we get 0. Well, is that what we wanted to get? Well, maybe, maybe not. Let's look up here. Ignoring the limit, if g of w equals g of z in this expression, then this thing will also be 0 because we're getting f of a thing minus f of the same thing. So this numerator will also be 0. And so this matches the value of f of g of w minus f of g of z appearing here, which is then, so let me emphasize, which is equal to 0. So this is kind of silly. We've introduced some crazy bailout condition here, and if the condition is not activated, then this is now a safe term, and this will be the value, and when we multiply this, it will still work. And if the bailout condition is activated, then this piecewise function will actually give us this value, but this value times 0, which will actually agree with what we had before. And so this means that these two, this really isn't equals, right? In fact, the limit is irrelevant for this equals, right? You can ignore the limit. I have safely changed the inner function here into an inner function, which is equal to the same thing by providing this bailout condition. So this is good news. Now I'm going to erase the blue. This is good news, but it's also kind of peculiar news, and it should make you suspicious. The reason I say this is peculiar is because it doesn't actually matter what I put here. And that's suspicious. If it doesn't matter what I put here, then I could easily have put a 0 here, and so far so good, this proof would still work. But it does matter in the end what I put there, of course, so we'll see later what we're doing about that. So let's erase the blue and continue. Now I'm going to split this limit into two limits. And let's see what happens. I'm going to write this really quick. So this is the limit as w approaches z of this ugly piecewise function, f of g of w minus f of g of z over f prime of g of z. And that's only if g of w is not equal to g of z. And it's f prime of g of z if g of w actually should happen to be equal to g of z, which is kind of the danger condition. So we're taking the limit of this function, and then we're multiplying it by the limit of the function g of w minus g of z over w minus z. And of course, the limit is as w approaches z. So I'm splitting the limit using the product law for limits. Is this justified? No, not yet, but that's okay. So long as I proceed to compute this and get a value, so long as I proceed to compute this and get a value, then we will, after the fact, justify the use of the product law for limits. So that's how those limit laws work. And this thing is super good news. This, of course, is g prime of z. And it's exactly the g prime of z that we expect to see in this proof. And so this term is free and clear. It's this term, which is kind of a mess. So let's have a close look at this term. Now, what on earth is going on with this term? First of all, we've got g of w and g of z everywhere. What's a constant and what's not? I think it will be useful here to just identify that g of z is simply a certain constant value, at least from the point of view of this limit. This limit is a function of w in an interesting way, but it is not a function of z. Z is a fixed value. And so what I want to do here is I want to go in and replace the g of z's with something that emphasizes that they are simply fixed values. So I'm going to go in here and I'm going to replace all the g of z's with, what should I use? I want to use something kind of neutral. I'm just going to use an alpha, okay? So everywhere I see a g of z, I'm going to replace it with an alpha. And all of these g of z's are going to start to look a little bit simpler. So here we've got f of alpha, and here we've got f of alpha. This is wrong. I wrote this wrong. I copied it wrong. So let me fix that first. That should have been g of w minus f of, no, minus g of z. So that would be the alpha. But I'm trying to write the alpha in purple. So let me get this right. Excuse me. All right, there we go. That's better. So just to recap, g of w minus g of z should have been transcribed this way, and the g of z should have been an alpha. So now I've just replaced all of the g of z's, and I'm going to make a little note here, star g of z is the thing that I'm writing alpha. Okay, now let's worry about the g of w's. The w actually only occurs inside a g. And that is very interesting. So let me just sort of sidebar, unrelated to this proof. Let's look at another example where we do something clever with algebra. So if you have something like a function like sine squared x minus 3 sine x plus 2 equals 0, and you want to solve this equation, it's really interesting here that the x appears only inside the sine function. And what you can do then is you can say, oh, well, this is like, let's let u equal sine x, and then this is u squared minus 3u plus 2 equals 0. If the x appeared here, for example, 2x, this kind of strategy would never work. But if the x occurs only inside some other function, then you can do a replacement and simplify things. Another way of looking at this is if you have a function and the variable x appears in the function, but only in the context of being inside some other function, then that function is a composition of two functions. It's the function u squared minus 3u plus 2 composed with the function sine. So the function sine is the inside, and this guy is the outside function. So whenever you've got a complicated formula and it depends upon a variable, but that variable only occurs in a certain context inside a function, then what you really have is a composition of two functions. And so what I want to do here is I want to take this beast, alphas and all, and I want to sort of recognize that thing as the composition of two functions. So the first function and the inside function from the point of view of that composition is going to be g of w. And the outside function, well, it's going to be sort of everything else. So here I'm going to introduce a new symbol, and the symbol will be u. And I will set u to be g of w. And let's do this in orange. So g of w is going to be u. And then I'm going to recognize this as an outer function with u's in place of those things, composed with an inner function, which is the function g. Okay, so that's what we're going to do to this thing in order to sort of rewrite and recognize it as a composition of two functions. So let's see what happens when we do that. I'll try to use my colors correctly, although it's going to be a bit of a challenge. So this is going to be the limit as w approaches z of a piecewise situation f of u, I'm trying to use my colors. I'll try. Let's see if I can do it. F of u minus f of alpha. That's going a little overboard, but let's keep it up. Let's keep trying. Divided by the function, and then we get u minus alpha, right? U minus alpha. And then here, we're just going to have an f prime of alpha as before. So that's f prime of alpha, which doesn't depend on u at all. And the conditions also have to get converted. So this, again, is if u is alpha, then we are in the first condition. And the second condition is if u is not equal to alpha. Okay, so the colors are driving me a little bit crazy. You get the idea. I think it's important to sort of distinguish. There are really two different substitutional acts here. And then this thing is getting composed with the function u goes to g of, well, u equals, so w goes to g of w really is the right way of writing that function. It's getting composed with the function w goes to g of w, which is u. So g of w is the value of u. So basically I have an inside function, which is the function g. And I think if I'm really just, if I'm not trying to use the colors to impress you, then I think the simplest thing to do here is to simply call this inside function g, because it is after all g, right? So let's just call this inside function g. And then this is the function, which is the function of u, right? So think of this as a function of u, and then the inside function is the function g, which takes w to the value g of w, which is what we're denoting u. So now this is the limit of a composition of two functions. Let's not forget here that we also have this stuff going on, but this is just, as we've already identified, g prime of z, and we don't need to worry about that term anymore. All right, so let's recap the last two steps because they're a little bit complicated. So in this piecewise function, we have identified that g of z is a constant, and we have simply relabeled that constant alpha, and that's in purple here, all of those substitutions. Then we have recognized that this thing is actually an interesting function of w. It's a very interesting function, though, because w appears only in the context of being inside a g. And so I've recognized that as a composition of a function with g. And I'm simply trying to say what function is composed with g. So basically, I'm taking all the g of w's and I'm replacing them with u. And now this is the function which composed with g will give you this thing. All right. Okay. Did that do anything for us? Well, yes, that's very, very good. So what we have here is a limit of a composition. Now, we don't have any exact laws that say, hey, whenever you have any limit of a composition, but we do have this law, which describes what happens when you have a limit of a composition. So this is a composition of two functions, f of g of x. So we should interpret here, this is a composition of two functions, but the variable is w. F of g of x, and it tells you what to do when you have a limit of a composition. Now let's check the conditions, the preconditions for this thing. We need the limit of the inner function to exist and equal a value. Okay, so do we have that? The inner function here is g. So what we really need here is for the limit of g of w as w approaches z to exist. Does it exist? Yes, because of this assumption. The assumption that g prime of z exists entails that g is also continuous at z. And if it's continuous at z, then the limit of that inner function g of w as w approaches z is equal to g of z. So this precondition for this compositional rule is satisfied because g is continuous, because g is differentiable at z, because of the assumption that the right-hand side exists. So far, so good. We also need f to be continuous at that limiting value. What is the limiting value of g as w approaches z? Of course, it's g of z by continuity. So is f continuous at g of z? Well, I don't know. Did we assume it? Yes, we did. Implicitly, we assumed it here because we took f prime of g of z is assumed to exist. And if f is differentiable at g of z, then f is continuous at g of z. And so the precondition for the outer function, which is this ugly function of u, it's not f in this example, it's this whole ugly thing defined piecewise. The precondition for that to be continuous is met, but not for the reasons I explained. So I screwed up. So here I'm arguing that f is continuous, but then I'm also reminding you that the function that we're worried about, the outside function, is not f. So I screwed that up. So the outside function that we're worried about is this ugly piecewise defined thing. It's that thing that needs to be continuous. And now I remember why I prepped this thing on the board, right? So excuse me for my mistake. So this thing is an example of this kind of situation, right? It is a difference quotient when we are not equal, and it's a derivative when we are equal. And that kind of situation is continuous simply because the derivative is the limit of the difference quotient. Okay, so this thing is continuous at g of z for these reasons. And that is actually, so it is related to the fact that f is differentiable at g of z, because notice, how do we know that the limit of this thing is equal to this thing? We know that the derivative is defined at alpha. And what is alpha? It's g of z. So really, we are using the fact that f prime of g of z exists. We're just using it to prove that this function is continuous because the limit of this is equal to this, because that's the definition of f prime of g of z. All right, so this precondition is met, this precondition is met. We may therefore do what is suggested here. We may evaluate the outer function at the limiting value of the inner function in order to calculate this entire ugly limit. So what we're going to do is, instead of calculating the limit, we're going to take f of y naught. We're going to take the outer function evaluated at the limit of the inner function. So let me remind you, the inner function is the g. The limit is as w approaches z, and the limiting value is the limit as w approaches z of g of z. That limiting value is g of z. So all I'm going to do is I'm going to take this ugly, colorful outer function, and I'm going to simply plug in g of z for that function. I'm going to abandon my use of colors, and I'm going to go over here, and I'm going to say, this is, well, f of g of z minus f of alpha if g of z is not alpha, and f prime of g of z if g of z is equal to alpha. So I'm evaluating a piecewise function, but I should no longer have this mysterious question of whether g of z is equal to alpha, because once I plug in a value to a piecewise defined function, you should be able to sort out whether that piecewise defining condition is true or false. Is it true or false? Alpha is the very definition of g of z, right? G of z has been plugged in for you, but alpha is g of z. And so this condition here, this condition is not met. This condition is met. G of z is equal to alpha. And so this thing is equal to f prime of g of z. So let's not forget, I also have a multiplication by g prime of z coming along for the ride. So that's times g prime of z. And finally, we get f prime of g of z times g prime of z is the derivative of f composed with g at c. And that's the chain rule. All right, there we have it.